For now, we are going to transition into our first technical session. I'd like to ask if your name is here on the speaker list, if you could please move up to the front with these seats here so that we can quickly move through these lightning talks. That would be much appreciated. So with that, I'm going to turn it over to the moderator for this session, Steve Ostoja.
Hi, good morning. So again, my name is Steve Ostoja. I'm the director of the USDA Climate Hub. We are here on campus at UC Davis. We've been here for 8 years. I've been here for 6. For those of you that are not from California or UC Davis, welcome. We're happy to have you here. I am the moderator of the first technical session. You can see the title there, Sustainable Agricultural Systems. There are a number of technical sessions. The problem that we're all up against, charged with applying solutions towards, have been wonderfully outlined by Christine Birdsong and then Felicia Marcus. That was wonderfully done. I'm not going to reiterate any of that. The intent here now is that you all, postdocs, graduate students, senior scientists, and everything in between, are part of the solution. We all belong here. The intent now is to survey what all is going on as part of this large integrated interdisciplinary research effort, multi-state research effort, so that we could get a sense of what all is going on and see where we can plug in, right? So this is, we've designed this very purposefully for that intent. There are going to be a series now of very short 5-minute talks with just a few slides, which we're going to do our best to enforce. And whoever comes up first, as you can see, Dr. Lauren Parker, who's a researcher in the Climate Hub, is going to introduce the next speaker. So that's how that's going to go. Lean in. If you're a graduate student, if you're a postdoc, and you see someone, introduce yourselves. This is our opportunity to exchange. We really want to facilitate that, and we've done, again, I'm going to say it again because it's important. We've designed this very intentionally to facilitate that. So with that in mind, I'm not going to read anything else on the slide. This is the first of the research themes, again, sustainable ag systems. We'll talk about socioeconomics and groundwater later in the morning or earlier this afternoon, and then extension education here after lunch. So with that in mind, I'm going to introduce the first speaker, Dr. Lauren Parker.
Thank you. Good morning. I'm Lauren Parker. I'm with the USDA California Climate Hub. Myself, along with Steve Ostoja and Ning Chung, make up the core of the climate team for the CAP. Our team's research objective is to identify the climate and ag water suitability and or vulnerability of key crops across the Southwest, given projected climate change. Our proposed approach addresses crop-specific temperature requirements, water demands, relative crop yields, and groundwater use to help us identify through a climate lens when, where, and under what kind of climate conditions we might expect to see crop-specific production maintained, reduced, or perhaps expanded. We're going to begin with almonds as a test case for this approach, but we do hope to conduct as much of the analysis as possible given information and data availability for a number of other high value and or high water demand crops across the Southwest, including pistachios, wine grapes, tomatoes, alfalfa, and pecans. So our first piece of the puzzle, this crop thermal niche assessment, uses phenology models that are parameterized with crop bioclimate requirements. So things like growing degree days, chill accumulation needs, or colder heat tolerances. And these models can be forced with projected future climate data to answer the question, from a temperature perspective, how suitable will a location be for growing certain crops under those future conditions? The same approach can also highlight the geographic hotspots for temperature-driven vulnerabilities to future crop production. Second, we're proposing to run a water balance model to estimate how much of the crop's annual water demands can be met by precipitation and soil moisture, and to use that value as a proxy for irrigation water demand at an annual time step. So the goal here is to address questions like how much irrigation water might be needed under future climate conditions, Given those anticipated changes in evapotranspiration, as well as potential changes in the timing and duration of a crop's maximal water demand as a function of the changes in phenology. Now, we recognize that future production is going to require both water efficiency and water savings. So we're kind of exploring some opportunities to quantify relationships between yield and crop evapotranspiration. And we hope to use these relationships to answer how relative crop yield changes under different deficit irrigation approaches. RDI might be one practice that folks can take to come up with some of that water savings. So we recognize this approach may not carry for all of our crops of interest. In fact, I had a meeting with some ARS research scientists and had some of my original hopes dashed just yesterday afternoon. So we'll see how it goes. It's probably not going to be as straightforward as I'd initially hoped, but that's how it happens, right? But it's an avenue that we're actively exploring. And then the last piece of our puzzle, also, as you can see here, not so well sorted out at this point, but we'd like to explore some opportunities to use groundwater models to ask questions that sit at this nexus of future crop water demands, irrigation water application, yield, and then our groundwater resources. The details, again, we're not there yet, but we're interested in understanding what proportion of future crop water demand might have to come from groundwater, but particularly given that future groundwater pumping will be limited, what would that lack of water mean for our irrigation strategies, our crop yields, just kind of trying to tie it all together. So that's my quick 5-minute brief overview of our proposed approach. Hopefully we'll have some results to share with you next year. If any of this interests you or you want to tell me all the reasons I can't do it, please reach out to me, leparker@ucdavis.edu. And with that, I'm going to turn it over to Cristina Lazcano.
Good morning, everyone. My name is Cristina Lazcano, and I'm Associate Professor of Soil Ecology at the Department of Land, Air, Water Resources. And so today I'm representing a team of faculty members in the Department of Land, Air, Water Resources, in the Department of Plant Sciences, and also at New Mexico State University, as well as postdocs and graduate students who are all working together in figuring out how soil health can contribute to the sustainability of irrigated agriculture in the southwestern United States. And here's my slide where I wanted to show you the pictures of all the team. We know that there are soil properties, specifically structure and the content of organic matter that help with water retention, also water infiltration, and in that way they could contribute substantially to resilience to drought events, but also to the recharge of aquifers during storms. And so in that way they could help with the sustainability of agriculture in California. There are practices like, for example, the use of cover crops that are well known to have a direct impact on these soil properties. But there are several uncertainties surrounding the use of these cover crops, especially in semi-arid climates like California. For example, how much water are these cover crops also using as compared to how much water they're contributing to store? What are the best management practices for these cover crops, right? In terms of termination practices, shall we use herbicides? Shall we mow the cover crop? Shall we use sheep, for example? Shall we integrate the cover crop into the soil by using tillage or maybe no-till? Or shall we fertilize the cover crops using compost, for example? And within this new framework of regenerative management, it's proposed that there are benefits of combining certain conservation practices, like, for example, the use of compost, the use of no-till, or the integration of sheep, and that it would be all of the combination of these practices would improve soil properties and soil health. But again, there are lots of uncertainties surrounding all of those potential benefits under semi-arid climates, not a lot of information. And so our objective is to determine the potential of management practices and healthy soils to contribute to the sustainability of groundwater, irrigated agriculture, and also the reduction of greenhouse gas emissions. And for that, we're going to do two things. First of all, a meta-analysis of published literature. We want to learn what is already done, and then we're going to do a survey of 30 commercial fields within California in annual and perennial crops to measure exactly soil hydrological properties and under different management practices. Thank you. So in objective 1, this is a little bit of a summary of where we are at. We are selecting conservation management practices that could have an effect on soil health, like no-till, the use of cover crops, crop rotations, use of perennial crops, and integration of livestock. And we're looking at the literature and looking at the value of certain soil health and hydraulic indicators. And this is an objective that we're working on right now. For objective 2, the survey of commercial fields, we're going to include some of the main crops grown in California, like grapes, almonds, and tomatoes. And we're going to select sites based on 2 criteria. One of them is the management, so we want to have a range from very regenerative to conventional. We're still trying to define what that means. And then the second criteria would be that there are sites that are suitable for groundwater recharge using this groundwater banking index. And finally, at some of these sites, we're going to install eddy covariance towers in order to be able to measure exchange of greenhouse gases and also water use of the cover crops. Thank you very much for your attention. I think I managed to be within time. And if you have any questions, there's my email and my website. Thank you.
Thank you. I'll be representing the water management team, which includes myself, Andre Dakach, Kelly Thorpe, and Matthew Robbie. If I had 30 seconds to summarize what the key takeaway is from the water management team, micro-irrigation and data-driven management can help growers cope with limited water and climate change extremes while remaining compliant with regulations. I'd like to highlight 2 growers that I think are leading the way to demonstrate how you can reduce your water use and still get economically viable yields. One of them is Cederquist Farms, which is a pistachio farm in Madera County. And this grower, out of his own initiative, started an experiment on his farm. He reduced water applied by 50%, and he wanted to know how much yield he can get with cutting back 50%. He did that by reducing the number of drippers on a drip line. And unfortunately, his name is Wayne Cederquist. He passed away unexpectedly recently. But before that, he had introduced us to his daughter, Karen Merino, who we are still working with. And you can see that even with 50% reduction in water use, the reductions in yield are not directly proportional. In 2020, the reduction in yield was only 20%, 27%. In 2021, with a 50% reduction in irrigation, the reduction in yield was only 14%, which makes us hopeful that growers can actually achieve the Sigma requirements or goals without catastrophic impact on irrigated agriculture. Another grower that I would like to highlight, who is in the audience today, is Kirk Pumphrey, who is actually an almond grower in Yolo County. Kirk uses 20% less water compared to almond water use in the Sacramento Valley, which ranges from 41 to 44 inches. In 2021, he used about 37 inches, and in 2022, by the way, these were drought years, he used 33.9. So he used 8% less water, even compared to last year. But compared to the average, he uses 20% less water. So the question then becomes, how does that impact his yield? Actually, it has not impacted his yield significantly. Kirk is here. You can ask him how that has impacted his yield. But I want to show you the recipe that Kirk uses to actually get to economically viable yield while using 20% less water. 3 things. Kirk, if you let me share your secret. One is micro-irrigation, high-frequency, low-volume applications. Applying irrigation every day in small amounts helps you to keep your crops without entering severe water stress that would impact yield. You have to have the technology, which we heard from the Undersecretary today, that programs like SWEEP are supporting. You need to have a variable frequency drive. The next one, which actually my colleague Patrick started, is a project on mulching. Okay? You can see the picture on my left. Kirk applied halm on hulls and shells, and we've been studying to see the impact of this. Mulching helps reduce soil evaporation and improves infiltration. Okay? And then the last secret is using sensors as feedback to dial in the irrigation. Now, on a larger scale, GSAs are looking for ways to monitor groundwater allocation, and they're using remote sensing because requiring a meter on everybody's well is not yet still valuable. But this issue is contagious, as you can see here in the press. There is still distrust in if this technology works. So our contribution is trying to ground truth this technology and also propose ways to improve satellite-based monitoring of groundwater allocation. We're also interested in understanding how cover crops impact water budgets at the field scale and at a groundwater basin scale. This is one of the sites you will visit tomorrow. It's a pistachio orchard with cover crops and without cover crops right on the same site. We're also working to understand management practices that impact groundwater quality, and that is important because programs like NRCS are interested in supporting programs that protect groundwater quality, and we are using technologies such as the deep better zone monitoring system to actually identify which practices are actually protecting groundwater from leaching of agrochemicals like nitrates or pesticides or any other chemicals in the ground. And this is just an example of some of the sites that we have installed in various crops. You can see here that when we had the 2 atmospheric rivers come through, we had a spike in nitrate leaching. I'd like to highlight some of the work of my colleagues. Kelly Thorpe at Maricopa is doing a lot of work on precision irrigation, improving water use in cotton and alfalfa, and as well as my work from my colleague Andre Dakach, who is doing a lot of good work on precision irrigation.
Karl.
Okay, we have in our group a number of folks whose names you see there. These folks are only one of the projects I'll be talking about very briefly. And the other folks are located at also at Fresno State. Sharon Venice will briefly describe her work. There's work also underway at New Mexico State, and is somewhat parallel to this work. In this particular project, an overall concept is being evaluated, and then some work is being done on selective dialysis to exchange to determine if we can improve some of the pretreatment efficiency, and also separate out toxic ions. Next slide, please. Oh, that's me.
I'll take care of
No, I'll do it. Okay. Well, I went through, right. How do I go back? I have a heavy finger. The use of non-traditional water supplies is work being done by the group on the slide you just saw, and also at New Mexico State. real quickly, we are focusing on using non-traditional water sources, given the fact that we are in a time when looks like, we've had droughts here, according to tree ring data, that have gone on for decades after decades. Who knows how long this one will last? But we have to find water, and water sources are comes in on various qualities, and brackish waters are, if it's too brackish, it can kill crops. On the other hand, if we can find ways to treat that water. It was mentioned this morning, there was a brief discussion on traditional irrigation practices versus the use of greenhouses. I would like to suggest that there's another alternative, and that's growing the crops in containers in a manner so that the water, the applied water, can be selected where when you have excess water, that water can be intercepted and reused and recycled. I've seen this tried in an experimental setting, and it was very successful. I understand the technology comes from Israel, and I think that that is something we need to look at because these technologies are going to add costs. There's no way around it. And part of the objective of our work is to find out what that cost is. And certainly, when we can intercept waters that have been used and reuse those waters, it's going to add value. So, moving on, this is the concept that we are working on at Fresno State. The circles on the left, the pre-filtration, and also the selective electrodialysis work is being headed up by Dr. Banerjees, who's in the audience. If you want to find out about those, go to the poster session. This is the work that's being undertaken at New Mexico State University. It focuses on a variety of source waters and improving ion selectivity for the electrodialysis system by membrane surface modification. Some very interesting work and important work if we're going to be able to improve on costs and efficiencies of these systems. And the work being done by Dr. Bennis, also covered by a poster session here, is focusing on, quite frankly, locating water that can be used. Dr. Bennis uses the EM38 soil salinity mapping and also Salinity 2 satellite imaging. Data that comes from these systems is used for the development of decision support tools, being able to not only locate but predict movement of the brackish water. And with that, thank you very much.
Patrick Brown.
All right, thank you very much. Sharon Bennis, who is also on this project, her work has just been addressed by Karl, so I'm going to skip over that. So I'm going to focus mostly on nutrient management. A lot of the processes we'll talk about will have relevance for water management, but also for salinity management. And this initial work is also co-funded by the Almond Board of California and the Pistachio Board of California. The objectives of this subset of activities in the project, they're listed there. It's really focused at the grower level and then scaling up to some of the larger meta-analyses and model work that others in this group are doing. So developing multi-scale sensing to go from the leaf and the soil all the way to the canopy and subsequently up to the modeled environment. Improving the quantification of physiological determinants of yield. I'll show you in the moment the context for that. improving early and mid-season yield prediction and spatial scaling of management. Then some forecasting work on plant dynamics and yield with AI modeling and precision farming. And then finally, sort of developing a system grower-focused to improve management decisions and management decision capability. All of this starts from observations we've been making over the years that yields across fields are incredibly variable. We tend, however, in agriculture, in almond agriculture, broad-scale agriculture, to manage at the scale of the entire field. If we are to achieve the next level, the next 30–40% of efficiency, this one-size-fits-all approach can't work. And if you look at this particular example here, which is nitrogen, and I've just broken the field down into the high-producing portions of the field and the low-producing portions of the field, and you have a difference there of almost 100 kilograms of nitrogen in demand from those different regions of the field. Now, historically, we have used a sort of an average approach. Now, most growers would actually manage to the maximum, not to the average. They are always looking to feed the hungriest portion of the field because that becomes a visual indicator of weakness, and the response is increase fertilization. If you do go for the average, which is what we have been proposing as a management, I guess you could argue you miss both ends, but on average you're better. There are some substantial constraints that almond growers face because most will have a single point of fertigation. So we need to develop mechanisms to improve our ability to manage at a scale that is essential if we're going to get that last 30–40% of efficiency. We've been working on this with the Ag Engineering Department, building individual tree monitoring capabilities. You can use that to develop the maps and then subsequently use that, of course, for site-specific management, which becomes more and more possible as we move to remote and driverless tractors and driverless spray rigs. One of the big constraints with current application technologies is tanks are filled with multiple products, hence you cannot have any specificity. Once you get a driverless machine, you can get the specificity. This yield monitoring allows you to answer that question of, certainly sensors are good and sensors can measure soil and plant capability, but if you can only afford 1 or 2 or 5 in a field, you don't know where to put them. And it is no better than an old-fashioned kick of the dirt. Then, of course, this ability gives you the capability to do experimentation in a far more sophisticated manner than possible previously. I'm hoping this slide doesn't play. We're working very hard on building this single tree capability. We'll jump forward. Here is a map that is a combination of data derived from single tree yield monitoring and extrapolation using modeling approaches to whole field variability. And one of the constraints we see in agriculture, in the tree production, is the extent of this variability is extraordinary. And if growers are to make a decision against this background without knowing it is there, it is rife with challenges. Of course, precision agriculture has overpromised in recent years, but I think there's reasons for that, and there's reasons to understand what this overpromise comes from. Not only has the occurrence of this variability been difficult to measure and monitor, you've got to go the next step and answer the question, just because I know there's variability, what is my return on investment as I attempt to manage it? And that is not trivial. Finally, it introduces complexity into the system, and the number one constraint for grower management decision is complexity. It's not necessarily knowledge, and it's not necessarily technology, so any solution has to address that as well. With that, thank you.
So it sounds like we have time for maybe one question. If anyone has a question for any of the panelists, Lauren can run a mic to you.
We all did so good at presenting. We've left you with no questions.
So with that, then we'll keep moving. I'll let I'll turn it back to Jen.
Yes, thank you all so much.